So anyway, and just to give you an idea how we compare, classical machine and versus a quantum computer. If we consider, for example, a bit flip in the classical gate, that's a NOT gate, and a two-bit gate goes, or a two-bit gate AND gate goes, it has the truth table on the right there. So when we play with our quantum systems, though, we think about different operations. So for example, when we can do a NOT gate, we can flip the bit, but in general, when we apply these rotations, and I use the word rotation because what you can think of here is a spin one-half particle in a magnetic field, and in general, the particle, when it's measured, it'll be pointing along the magnetic field. This could be an electron, for example, against the magnetic field. But in general, of course, we put it in a superposition state, and so and if we call those two states spins, or you can just label them 0 and 1s, which is more conventional. But anyways, but when we apply an operation, it's like taking this spin one-half particle, and we're able to rotate it at any angle. So in other words, it's not a discrete operation. We can put it anywhere on this so-called block sphere. So and the other thing is we can, it turns out an analog to a two-bit AND gate in a classical computer is one simple two-qubit logic gate that we use a lot is it's called the phase gate, and basically it's you can see the truth table that the 1-1 state gets a minus sign on it in front of it, so we call it a phase gate because -1 is e to the I pi, and so it's that phase of pi that's why we call it a phase operation. So anyway, but of course, if we apply these gates to the simple rotation and then we apply this operator, the two-qubit logic gate, we end up with a state like this. It puts a minus sign in front of this coefficient, and this state is now, and we call it entangled because we can no longer write the two-qubit state as a product of the two separate states at once. Whereas, whereas for the initial state, we could do that. Here we could write it as a product of the two qubit states. But now that we've done this operation, the qubits are entangled. We can't talk about a single